Assalamualaikum warahmatullahi wabarakatuh. My name is Adib bin Muhammad Nawar, and I'm going to present to you about the probability distribution in financial modeling. And we're going to have three problems, and I'm also going to show you how to calculate it on Microsoft Excel. So this is the first one, problem one, which is the binomial stock price and option payoff problem. So the first question is, a stock is currently priced at S initial equal to RM 100 ringgit. Over one period, its price can either move up or up to U as 0 or down to D as 0, where U equal to 1.20 and D equal to 0.85. The probability of an upward move is P equal to 0.6. And we have two questions here. And the first question is, calculate the expected logarithm return EY and the variance of the log return for this stock over a single period. And the second question is, a digital binary option only pays out 100 ringgit if the stock price moves up, but pays nothing if it moves down. Based on the Bernoulli's distribution properties, calculate the expected payoff and the variance of the option payoff. So to calculate it, we need to find the logarithmic return y, and it is defined as y equal to natural log S1 over S0, and its initial parameters is current stock price, S0 equal to 100 ringgit, upward multiplier equal to 1.20 with probability P 0.6, and downward multiplier D equal to 0.85 with probability 1 minus P equal to 0.4. And for the step 1, we need to calculate the log return for each state. And for the outward state, y up is equal to natural log U S0 over S0. And it is equal to natural log 1.20, and we will get and the estimated value around 0.182322. And for the downward state, we use the same formula, and we will get an estimated value around negative 0.16519. And then for the next step, we need to calculate the expected logarithm return EY, and we will use the formula P times y up plus 1 minus P y down, and we will get the value of 0.044385, or we can say 44%. And for the final step, we need to calculate the variance of the log return y, and we will use the algebraic shortcut for a binary outcome distribution. And this is the formula: P times 1 minus P times y up minus y down squared. And we insert all the value, and we will get the value at estimation around 0.028540. And for B, we're going to let x be the random variable representing the option payoff. And for the upward move, x up equal to 100 ringgit with a probability of 0.6, and the downward move, x down with the probability with equal to RM0 ringgit with a probability of 0.4. And because this rely on a binary choice, it can be modeled as scaled Bernoulli's distribution properties, where x equal to 100 times b, and b is estimated Bernoulli's 0.6. And to calculate it, we're going to have two steps. The first one is to find the expected payoff EX, which we will use the formula of P times X up plus 1 minus P times X down. We just insert all the value, and we will get the expected payoff of 60 ringgit. And the second step is to find the variance of the payoff variance X by using Bernoulli's variance properties. As you can see there, is P times 1 minus p, we're going to get this variance x equal to 100 squared times variance b equal to 10,000. And for variance, and to find its value, its final value, we're going to change the variance b, which is we already know is 0.24, and we'll get the final answer of 2,400. So we're going to continue the problem number 2, which the portfolio risk normal distribution problem. We're going to assume the logarithmic return of a market portfolio is driven by a Gaussian normal distribution with an expected annual return of 8% and a volatility of 15%. And we got two questions. And A, we have using the empirical properties of the Gaussian distribution, determine the approximate intervals within which 2 over 3 times 60%, 67% and 95% of the portfolio's annual return outcome will fall. And the second question is briefly discuss why assuming a perfect Gaussian world might underestimate risk during extreme market crashes like 2008 financial crisis. So this is the parameters given. We're going to have the expected annual return 8% and a volatility of 15%. Okay, for the question A, we're going to have two methods, and the first method is empirical rule breakdown. And for the and it is the first method is actually an approximation, and for one sigma interval, we're going to calculate it using m plus minus one standard deviation, and we're just going to insert all the parameters given. I will get 7%, negative 7%, I'm sorry, and 23%. And for the 2 sigma interval approximation, we will get negative 22% and 38%. And these 2 sigma interval, we're just going to change the 1 into 2. And as for method number 2, we're going to use exact theoretical interval by using precise z-score. And for the exact 67% interval, z we're going to have approximately 0.9741. And as usual, we're just going to enter the value of the 8% plus minus the z value alongside with its volatility. We will get the answer. And the first one, we will get the negative 6.61% and 22.61%. And for the exact 95% interval, we're going to use Z approximately around 1.9600. And we're just going to use the same formula, and we will get negative 21.40% and 37.40%. Okay, and as for the question D is to briefly discuss why assuming a perfect Gaussian world might underestimate risk during extreme market crashes like the 2008 financial crisis. So we're going to explain it one by one. We got three, and the first one is the fat tails, leptokurtosis, and the real world asset return exhibit fat tails, meaning extreme negative event occurs far more frequently than Gaussian bell curve expects. In the normal distribution, a 6 sigma or 7 sigma event like the 2008 crash is mathematically calculated to occur once every few billion years. In reality, market crashes happen every few decades. And as for the second one, we're going to have a flaws in value at risk. For the traditional risk models utilize parametric value at risk built in standard normal boundaries. This approach tells you the minimal loss threshold at a certain percentile but completely fails to measure the catastrophic severity of losses hidden beyond that threshold, which the tail risk. And then the third one is the systemic feedback loops and liquidity evaporation. The Gaussian model assumes market events are continuously continuous and driven by independent data points. During a financial panic, investors' behavior synchronizes. Asset correlation rapidly converges to one, forces liquidation, triggers margin calls, and market liquidity vanishes overnight. This creates a cascading downwards spiral that a rigid normal distribution cannot track. And then we're going to continue with problem number three, which the microstructure asset pricing problem. And here's the question, which is a high frequency trading firm models the arrival of buy market orders using a Poisson distribution. The average arrival rate of buy orders is lambda equal to 4 orders per millisecond. And the first question is the state the expected value and the variance of orders arrival per millisecond of this asset. And the second one is the calculate the exact probability that the firm receives exactly two buy orders in each milliseconds. So to find the expected value and the variance, we're going to look at the parameters given, which is the lambda equal to 4 bytes orders per millisecond. And by design, one of the unique properties of a Poisson distribution is that its first moment, which is the mean, and its variance are both perfectly defined by its rate parameter lambda. So by knowing this, know we can know and state the value each value. For the expected value, is equal to lambda and is equal to 4 orders per millisecond. And for variance, it's also the same. By using lambda, we got its value of 4. Okay, and then for the second question, which calculate the exact probability that the firm received exactly two buy orders in each millisecond, and we're going to calculate the exact probability using the Poisson mass function. This is the formula, and we're going to apply it to get the value, the probability. So this is the solution. And first we substitute the parameters that we already know, which is lambda equal to 4 and k equal to 2. So when we substitute it, we're going to get the answer of 8 times exponent negative e. So how to get this? We're just going to use our calculators and get its estimation value and times it with 8, and we'll get the final answer of 0.146525, or we can say it's 40.65%. So for task number 2, we're going to develop an interactive spreadsheet, which I'm going to use in Google Excel, Microsoft Excel, to create an interactive calculator where a user can input changing variables, which is all these variables, and utilize in statistical function like binomial distribution, normal distribution, and Poisson distribution in Excel. And this is for the problem 1 spreadsheet that I already created. And this is for problem number 2 spreadsheet that I already also created. And finally, this is the problem 3 spreadsheet.
This meeting is being recorded.
Okay, so this is the complete design calculator. So I'm going to show you how to use it. So all we need to do is just simply add all the value. For the initial stock price, we're going to enter 100, and for its multiplier is 1.20, and for downward multiplier is 0.85, and for upward probability is 0.6, and for option payoff is 100, and for downstate is 0. So we get all this value, and this is all the formula that I use. Okay, now moving on to problem number 2. So do the same. We're going to do the same thing. All we need to do is insert all the numbers, 0.08, and for annual volatility is 0.15, sorry, 15, and we get all the value. and this is all the formula that I use. Okay, and finally moving on to problem number 3. So problem number three, I'm going to use like the same thing. I'm going to just insert all the value that is already given. For lambda is 4, and for target order arrival k is 2, and we get all the values. And I'm going to show specifically like what the question told us to use these two. For row 11 and 12, I use that formula, as you can see. And for problem number 3, I use Poisson distribution to get the exact probability. Assalamualaikum warahmatullahi wabarakatuh. My name is Adib bin Muhammad Nawar.